M slab. Experiment No. 0.7. Analog to digital converter, ADC. Objectives: to understand the basic theory of analog to digital converter, ADC. To understand the basic operation and characteristics of ADC0804. To implement analog to digital converter using ADC0804. Equipment required: DMM breadboard DC power supply plus 5V, fixed, resistors 150 ohms quantity equals 8, 2K ohms quantity equals 2, 10K ohms quantity equals 1, potentiometer 10K ohms quantity equals 1, 500 ohms quantity equals 1, capacitors 150 pF quantity equals 1, 0.1 UF quantity equals 3, LEDs red/green color quantity equals 8, IC, ADC0804 quantity equals 1, connecting wires. Theory: analog to digital converters, ADCSORA/converters, translate ferrometallic. Measurements currents, 2, which are usually continuous voltages or digital. Words used in computing, data transmission, information processing and storage and control system set. Wedo this conversion, because digital signal series to store debug, using a variety of encoding techniques, and Daryl most free from was. The operation of analog to digital, ADC, converter. Figure 7.1 shows the transfer characteristic of an ideal 3-bit ADC. The analog input range from 0 to 1V quantized by dividing this continuum into 8 discrete levels, ranges. All analog values within a given range are represented by the same digital code, which corresponds to the nominal mid-range value. Therefore there is an inherent quantization uncertainty or quantization error of plus or minus 1/2 least significant bit. In the analog to digital conversion process, only way to the LSB, this quantization uncertainty of bits. The num errors to increase the reduces the smallest quantization value or quantum, Q, analog difference which can be solved or distinguished with ADC. It can be expressed as equals 7.1. Figure 7.1, transfer characteristics of ideal 3-bit ADC. Here Fs is the full scale range which is equals to and tunis the resolution determined by digital output bits and thus greater the value of higher will be the resolution. In general ADC manufacturers indicate the resolution in unit of bits. For example, their solution of ADC0804 is expressed by 8 bits in technical manual. There are a great number of circuit designs for A/converters such as digital ramp, successive approximation, flash and tracking types. The successive approximation is the inlet type of ADCs in our experiments, whether for introduce the operation of successive approximation as follows. Figure 7.2 shows the block diagram of 8-bit successive approximation ADC. The normal operation proceeds as follows. The sample and hold, SNH. Circuit is set to retent analog input voltage, 6, that was percentage of n time before the conversion starts and maintain it constant to avoid any change during the conversion period. The control logic sets the most significant bit, MSB, D7 of register to 1. With L other bits to 0. The digital to analog converter, DACORD/A, converts the binary code as into an analog output V, D, and which can be evaluated by, equals 7.2, theta output V, D, is just a half of the interference voltage, VREV. The comparator compares the V, D, with the analog input, 6. If 6V, D, the 1 remains in D7. If 6. Figure 7.2 the block diagram of successive approximation ADC. ADC0804 analog to digital converter. The ADC0804 which is a 20-pin dual in-line package is an 8-bit AD which operates on the successive approximation principle. Its major characteristics include single 5V. Power supply 0V to 5 range 15 M1 analog input voltage power dissipation at time Since the 100 US conversion resolution of ADC, the analog input is divided into 28 or 256 discrete ranges. 0804 is 8 bits with 5V reference voltage. Each range represents 5/256 equals 0.01953V. Thus the digital output code 0000000000H corresponds to an analog input voltage of 0.00V, and 11111111, FFH, represents 4.9805V. The unadjusted error, which contains full-scale, off-stand nonlinearity errors, is plus or minus 1 ls for 0.01953V. Figure 7.3 Pin configuration of ADC0804. The connection diagram of ADC0804 is shown in figure 7.3. When data stored from the output port D0 D7. The combination of both and being low will enable 3 stat output latch to provide 8-bit digital outputs. E04 is shy the outputs D0 to 7 will be floating. The ADC0804 converter is started B and having simultaneous low. This resets the 8-bit register. When goes to high, the converter starts the conversion process. The CLKIN, pin 4, is the input pin of clock pulses whose frequency can be from 100 to 800 kHz. The pin remains shy during the conversion and will make a high to low transition if the conversion is completed. The analog differential input voltage is applied to the pins VEN, plus, and VEN, if a single end input is desired, the VEN, should be connected to ground. The AG end is the ground for analog signal and the DG end is for digital signal. Notice that the reference voltage is either a half of the voltage which is applied to the weak pin or is equal to the voltage which is externally forced 8th ref/2 pin. ADC0804 has a built-in Schmitt triggers shown in figure 7.4. Figure 7.4 Internal clock generator of ADC0804. The clock for the ADC0804 can be derived from an external source connected to CLK in pin 4, or an external RC network can be added to provide self clocking. As shown in figure 7.4, an external R network is connected to pin CLKR, pin 19, and CLKIN, pin 4, to provide the clock for the ADC. The clock frequency can be found by Hertz. 7.3, figure 7.5 shows a analog to digital converter with the ADC0804. The analog input signal is connected to VEN, plus, input and the amplitude is controlled by VR2. Another input VEN, is connected to ground. The reference voltage to the ref/2, pin 9, is provided B plus 5 with the voltage divider containing RL R2 and VR1. The combination of C1 and R3 determines the clock frequency. The pin 1 and pin 2 are directly connected to ground to enable the ADC. For convenience, the pin 3 and pin 5 are wired to switch SW1 in order to simulate the control signal. Figure 7.5. The circuit diagram of ADC0804. Procedure analog to digital converter, ADC0804. A. Construct the circuit of figure 7.5 on the breadboard. B. Using DMM measure the voltage, ref/2, at pin 9 and slowly adjust the VR1 until the measured voltage reaches 2.5V. This is the ADC0804 analog voltage input range from 0 to 5V. C. Measure the analog input, pin 6, and slowly adjust the VR2 until the measured voltage reaches 0V. D. Observe and record tested as off LEDs LED on equals 1 LED off equals 0. E. Adjust the VR2 to G. The analog input voltage is listed in table 7.1. And repeat step. F. Fill table 7.1 accordingly. Table 7.1. Status of LEDs analog binary digital output input senior. Calculated values, measured values, voltages no. V, D7, D6, D5, D4, D3, D2, D1, D0, D7, D6, D5, D4, D3, D2, D1, D0. 10.0. 20.5V, 31V, 41.5V, 52V, 62.5 V, 73 V, 83.5 V, 94 V, 104.5 V, 11.5 V,